Okay, so we have seen the so we are talking about data structure for a dynamic set of sets, I mean multiple sets. So, in the last class we have seen one solution. So, basically we have given, so what is the problem? We have given some sets of sets Sk, there is a R set, and so this is dynamic set, that means we can we can insert any set. So, we are looking for a data structure for this dynamic collection of sets such that we should able to perform the operations like make set. So, we have given element x, we should able to, so from this Si there is a element which is called rep of Si, representative element, which is representing the whole set Si. Now, make set is basically we are x is not belongs to any of these given any of the sets. So, this we are going to add this we are going to add this collection, and the rep of this is basically because there is only one element. So, this is one operation, another operation is find set. So, we have given an element. So, we want to return the set where this element is belonging. So, in order to return the whole set, we can just return the representative element. So, we return the rep of Sx where x belongs to that set. So, this is the operation, and then the union. So, we want to do the union of x y. So, we have given two elements, say x belongs to Sx and y belongs to Sy. Now, we want to replace Sx and Sy by their union. We replace Sx and Sy by Sx union Sy, and we want to have a representative element of this this new Sx union Sy set. So, this is the three operations we need to perform. So, we have seen one data structure, that is the doubly connected linked list. So, we represent each Si. So, say Si is say x1, x2, xk. So, this we have seen, we use a x1, sorry, so x2, xk. So, dot dot dot. So, this is basically null, this is null. So, this is the way we represent a set. So, using a doubly connected linked list, we have seen in the last class this data structure, and representative element is the first element of the first node, the first node. So, this is a unordered list because the sets is itself is unordered. So, this is an unordered list. So, this representative element is the first element of that first node, the value of the first node. So, that is x1. So, this is the way, and we have seen how to make a set. Making a set means we just create a node, and this is a basically collection of doubly connected linked list. So, this is a data structure we are using, and then we have seen the find set. Find set means we know the position of that x. So, we go there and we traverse the list and we back to the first element and we return that. And union means we have added the another doubly connected linked list. So, for that also we need to travel. So, this find set and union took us order of n times if the size is n. So, now we want to think how we can do it in better way, like at least log n time. So, for that we know any data structure which can give us log n performance. So, what about balance tree? So, we can think for a simple balance tree solution. So, let us, this is the second proposal, simple balance tree. Balance tree. So, this is the second proposal. So, one balance tree we have seen in our class, that is red black tree. This is a balanced tree. So what about what? So the idea is whether we can use the balanced tree for our set. So suppose, so how we can do that? Suppose we have a set Si, which is basically say x1, x2, say xk. So we want to have a tree for this, and which is a balanced tree. So we do not care about the key value, because this set is unordered. So there is no, we ignore the, so this is the unordered set. So there is no ordering of this element. So there is no question of say binary search tree property, because we there is no ordering of the element. So this key, we are ignoring the key value, ignoring the key, this key. So once we form this red black tree, we have a key value, and based on that key value we form the binary search tree property. I mean, any node in the left subtree is less than the key value of that root, any node in the right subtree is greater than the key value. So that we are ignoring the key value, because the set is just a unordered collection of disjoint element. Okay. Distinct element is set. So now, so we have a tree. So we just make a balanced tree. So we have a balanced tree, while we are don't bothering about the value of these nodes, because this is just unordered collection. So but the structure should be balanced. Okay. And then what is the representative element? So representative element can be the root of the tree. So that is the way. So for example, suppose we have given this set, say 5 elements, say x1, x2, x3, x4, x5. Okay. So now how to form a tree? So suppose this is x1, and we do not care about the value, because this is unordered list. So x4 can become here, x3, we just do care about the structure. This tree should be balanced, the height should be log n, x2, x5. So suppose this is our Si. Now what is the rep of Si? Rep of Si is basically the root. Rep of Si is basically x1, root of the element. So this is our data structure. So we just make a balanced tree with this another list, another with these elements, and we just ignore the key. So but the structure should be balanced, height should be log n. Okay. So this is our proposed data structure. Now we want to see how fast we can perform those 3 operations, like make set. So how to make set? So how we can? So first operation is make set. So we have given an element x which is not there in the collections. So we want to create a set, we want to insert a set in, this is the insertion operation in that collection script S. So this is basically we just create a node, that is it, we just create a node x. This is a single node tree, just create a node, and this is the rep of this x is basically the first element, this is root is x itself. So this is the way. So what is the time complexity of this? Constant. Okay. So now we want to see how we can do the find set, find of x. So find of x take how long time? So find of x means, suppose we want to find the, so suppose this is our x5. Okay. So we know the position of this. So now we have to return the representative element of this. So how to return the? So we have to we have to reach to the we have to go to the parent of this, then parent of this. So, we return the x 1. So, that is the operation for find set. So, we want to return this S I, because we know x is belonging to S I, x is say x 5. Now, we have to return this x 1, x 1 is the root of that. So, in order to reach to the root, what is the time? Time is log n, because this is a balanced tree. So, this will take log n time. Okay. So, find operation will take log n time, because we know the x, say we want to find the set where x 5 is belonging. So, that is basically that is basically this tree. Now, we have to return the representative element of this, that is basically the root. So, to reach to the root, we have to go to the height of this tree, because this is the balanced tree. So, this is log n. Now, how to perform this union operation? So, that is that also we want to see whether we can do it in log n time or not. Okay. So, union. So, suppose we have two elements x and y. Suppose say x belonging to the set and y belonging to another set, and we want to replace these two set S x and S y by their union, and we have to. So, how to do that? So, suppose this is our S x, this is our S x, S is somewhere here, and we have another set, say S y. So, this is say S y. So, this is say y 1, say y 2, y 4, y 5, y 6, something like that. So, we have two sets S x and S y. Now, the question is how we can merge these two sets, how we can merge these two tree, and in order to get a balanced tree again. So, you have to get the ultimately this union should be a set, and union is a set, and that is also be a tree. So, that has to be balanced. So, what is the proposal? So, we can think of having say so how we can merge these two set. So, we can have a new root, like we can have this element over here, then we can do like this kind of thing, or else we can just so this is already a balanced tree. So, we can just keep on insert these nodes. So, we have y 1 y 2 like this. So, we can insert this node into this tree. So, that again will take n log n time, because if there are n elements in the set y, order of n element, then this itself will take n log n time, but we want to do it in log n time. So, that is the idea of concatenation. So, if we have a two red black tree, so that is the idea of concatenation, like so this will do the concatenation of two trees, concatenates this two red black tree. So, like we have this tree, we have a bigger tree, it is say this is S x, we do not know S y may be bigger. So, for example, this is another tree S y. Now, we can add this tree over here by concatenate operation. We have seen this operation in the red black tree. So, this is basically this will take and this is basically we have just concatenate this tree over here, and this will take log n time, the height of this tree. Okay. So, basically we take this element, then we search the position of this element. So, this way we will do. So, this will take log n time. So, this is the concatenate operation. So, this is log n time. Okay, but so this is the logarithm time we are doing. So, now we want to do something better on this, like we want to build a we want to do log n time. How we can achieve a log n time? So, this is what we are going to do now, is called data structure augmentation. So, we want to augment our data structure, so that we can do the operation in faster way, okay, in a amortized sense. So, we want to do lots of amortized analysis. So, there we will see how we can get log n, log n. Okay. So, this is the next things we will discuss. This is the, let us give an outline of this, what we are going to do, that is called plan of attack. So, this is sort of outline what we are going to do, I mean how we can. So, this is basically branch of augmentation we will do in our data structure. So, basically we have two basic data structure, one is W connected linked list, another idea is the tree. Here it is a red balanced tree. So, we will see a general tree, okay. And then we will see how we can augment this to data structure, and we will see, we will do some amortized analysis in order to get the performance in log n, log n, like this. So, the idea is to we will build a simple disjoint union data structure that in amortized sense, we will do the amortized analysis, amortized sense perform significantly better than log n, perform significantly better than log n per operation. So, we have basically 3 operations. Okay. So, we want to make it faster on these 3 operations, like make set is always constant. So, that we are not bothering, but other 2 operations like find set, for the W connected linked list, find set will take order of n time. So, now the question is how we can do some sort of augmentation, or how we can do some. So, after augmentation, how we can do the analysis, amortized analysis to get it log n, not only log n, log n operations, even better than log n. So, log n better than log n is means log n and so on, but not constant, because log n. So, it is not constant basically, but it tending to. So, this log this we have seen in one data structure. What is that? The Van Emne-Boas data structure. Okay. So, there we have seen the fixed universe successor problem. So, there we have seen log u, but there we have used 5 tricks to achieve that, but here we are going to use the 2 tricks only to achieve this. Okay. So, to reach this goal, so this is our goal. So, to reach this goal we will use 2 tricks. This goal we will introduce through tricks. Okay. each tricks convert this operation from theta n to log n. Okay. Each trick convert a trivial solution theta n solution to solution into a simple log n solution. So, that is the goal, simple log n solution each of this trick. So, theta n solution means we have seen a W connected linked list. So, how we can but this will be in amortized sense, this analysis is amortized analysis. So, we will talk about that. Okay. So, first trick is on this W connected linked list, we will do some augmentation on this W connected linked list and then we will apply this trick. And the second trick is on the tree. So, we will apply this trick on the tree data structure. So, let us talk about first trick, I mean let us go back to the data structure which is we use for on the W connected list. So, this is the we will do some augmentation. So, augmentation on the linked list. So, we have a linked list solution, this is basically W linked list. So, W linked list, we will do some augmentation in the W linked list, data structure augmentation to have the better performance on these operations like okay. So, just to recap, so we have a set Si. So, this is x1, x2, xk. Now, what is our data structure? Our data structure is just simply a W connected linked list. So, x1, so this is our Si. So, x2 dot 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 xk. So, this is basically this is null, this is null. So, this is the data structure we have used, this is the W linked list we have used for our this problem. Okay. Now, we have seen for this data structure, suppose we have a node. So, what is the find operation? Find set of x, suppose x is here. So, we know the position of x. So, now to reach to the representative element, what we did? We have to come back to the beginning. Okay. So, that was taking log n time. So, now how we can augment this in order to achieve this in a constant time. So, how to augment this data structure, so that we can achieve this in a constant time. So, any idea how we can make this operation find set faster, I mean theta of 1 time instead of theta of n times. So, we have to do some augmentation in this list. So, what we do? So, what if we store each element, in each element other than this we store the representative element, that means each element we have a list to the beginning. So, we have a we store the pointer of the first element. So, this is the augmentation we are going to do for our W connected list. So, we store the each element xj, each element xj also store pointers pointer, and that pointer is called rep of x j pointer to rep of s I. So, that is basically the first element. So, we are storing the pointer of this s j. So, each of this will point to the first element. So, that then the find set is easy. So, if we have a link from this to this, so suppose this is x. So, now to get the representative, we just take this pointer and we take this x 1. So, that will return. So, that will find set will take constant time. Find set will take constant time after doing this augmentation. So, this is not a amortized analysis, this is the exact analysis. So, this will take constant time. Now, we want to see how we can manage the union. We have already seen make set that is constant, we are not bothering about that. So, we will see how we can manage the union operation. So, that is our next discussion, how we can achieve the union operation, how we can perform the union operation of these two sets. So, what type of augmentation we will do, because for union if you have another set y. So, if we have another set y, so say y 1, so this is say we have say 2 element in this set. Okay, so this is only 2 elements say x, and we have a y which is say 4 element. So, this is also a doubly connected linked list. So, this is S x. So, this is say x, and this is somewhere y is there. So, this is S y, this is y 1, this is the representative element of S y. Now, we want to do the union of x comma y. So, for union what we are doing? We are just linking this to this and this to this. This is the union operation we are doing. So, for that what we have to do? We have to go back from here to here. So, but we have the link for this. So, that way we can, but we want to do further augmentation. So, that how to now if we just join this like this, then again we have to, for all this element we have to go to the beginning. So, this will take again linear time if the size of this is linear. So, anyway, we will continue this in the next class. Thank you.